Have you ever wondered why our planet isn't a perfect marble floating in space? Or how a colossal waterfall seems to flow upwards, defying the very law that's supposed to pull it down? And what about the silent, towering giants of our world trees? How do they manage to drink water from the ground and pull it hundreds of feet into the sky? These aren't magic tricks. They're some of gravity's most fascinating and bizarre oddities. Today, we rate peeling back the layers of our everyday world to uncover the extraordinary physics hiding in plain sight. Welcome to a journey where gravity gets weird. Let's start with our own home, planet Earth. From space, it looks like a beautiful, smooth blue sphere. But this is a bit of a cosmic illusion. In reality, Earth is what scientists call an oblate spheroid. That's a fancy way of saying it's a bit chubby around the middle. Why? It all comes down to a cosmic tug of war. As Earth spins on its axis, it generates a centrifugal force. Think about spinning on a carousel. You feel a force pushing you outwards. The same thing happens to our planet. This outward force is strongest at the equator, causing the planet to bulge. The diameter at the equator is about 43 kilometers, or 27 miles, wider than the diameter from pole to pole. So, if you were to stand at the equator, you'd actually be slightly farther from the Earth's center than if you were standing at the North or South Pole. But the story gets even stranger. If we were to remove all the water from the oceans and ignore the mountains and valleys, what shape would Earth be? You might think it would be that smooth, slightly squashed sphere. But it's not. It would be a lumpy, bumpy, potato-like shape that scientists call the geoid. This is the true shape of Earth's gravity field. The geoid represents the surface where gravity's pull is equal everywhere. The lumps and bumps on the geoid are caused by the uneven distribution of mass inside the Earth. Areas with more mass, like dense rock formations deep beneath the surface, have a stronger gravitational pull. This pulls more water towards them, creating a hill in the ocean's surface. Conversely, areas with less mass have weaker gravity, causing a valley. These gravity anomalies mean that the direction of down, the direction a plumb bob would point, isn't always straight towards the center of the Earth. It can be slightly skewed by these massive, hidden structures beneath our feet. So, the ground beneath you isn't just ground, it's part of a complex, dynamic system of gravitational highs and lows, a hidden landscape that shapes our entire world. It's a reminder that even the most fundamental force we know is full of subtle and surprising variations. Now, let's journey from the shape of our planet to one of its most breathtaking features, waterfalls. We see them as the ultimate display of gravity, as power trillions of gallons of water, surrendering to its pull, crashing downwards with immense force. But look closer, especially at the base of a mighty waterfall. You'll see something that seems impossible. Water and mist rising, dancing upwards, seemingly defying gravity. How can this be? This isn't an illusion. It's a beautiful demonstration of fluid dynamics and energy transfer. As the massive volume of water plummets, it gains incredible speed and kinetic energy. When this water crashes into the pool at the bottom, that energy has to go somewhere. A huge amount of it is converted into sound, the deafening roar of the falls, and into turbulence in the water. But a significant portion of this energy atomizes the water, shattering it into a fine mist of tiny droplets. At the same time, the falling column of water acts like a giant piston, dragging a huge amount of air down with it. This creates a powerful downdraft. When this air hits the base of the falls, it has nowhere to go but outwards and upwards, creating strong, turbulent updrafts all around the plunge pool. These updrafts are powerful enough to catch the fine mist and even larger water droplets, carrying them high into the air. This is what creates the cloud of mist that perpetually hangs around large waterfalls, often rising hundreds of feet, creating its own microclimate and nourishing lush vegetation on the surrounding cliffs. So, what looks like water-defying gravity is actually a complex interplay of forces, the kinetic energy of the falling water creating mist, and the powerful updrafts of air giving that mist a lift. It's not a fight against gravity, but rather a partnership with other forces of physics, creating one of nature's most spectacular displays. It's a perfect storm of energy, air, and water, all choreographed by the unyielding laws of physics. From the thunderous power of waterfalls, we turn to the silent, patient strength of trees. Consider a giant redwood, standing over 300 feet tall. That's taller than a 30-story building. Every day, this tree needs to transport hundreds of gallons of water from its roots, deep in the soil, all the way to its topmost leaves. How does it do it? It has no mechanical pump, no moving parts. This has been a botanical puzzle for centuries, but the answer lies in a remarkable property of water itself, powered by the sun. The process is driven by something called transpiration. Think of it as trees sweating. The leaves are covered in tiny pores called stomata. When these pores open to take in carbon dioxide for photosynthesis, water vapor escapes into the atmosphere. This evaporation from the leaves creates a negative pressure, or a suction force. This is where the magic of physics kicks in. Water molecules have a strong attraction to each other, a property known as cohesion. They like to stick together. They also stick to the walls of the narrow tubes inside the tree that transport water, called xylem. This property is called adhesion. Together, cohesion and adhesion create a continuous, unbroken chain of water molecules, stretching all the way from the leaves down to the roots. As one water molecule evaporates from a leaf, it pulls on the next one in the chain, which pulls on the next, and so on, all the way down. This cohesion tension mechanism works like sipping water through a very, very long straw. The pull, or tension, generated by evaporation at the top is strong enough to lift the entire water column against the force of gravity. The xylem vessels are incredibly narrow, which is crucial. This narrowness enhances the adhesive forces and prevents the water column from breaking under the immense tension, which can be equivalent to the pressure needed to inflate a car tire. So, the secret isn't a pump pushing from the bottom, but a powerful pull from the top, driven by the sun's energy. It's a silent, passive, yet incredibly powerful system, a testament to the elegant solutions nature has evolved to work with and seemingly overcome the fundamental force of gravity. So, the next time you look at a map of the world, stand at the foot of a waterfall, or rest in the shade of a tall tree, remember the hidden physics at play. Our planet is not a simple sphere, but a lumpy geoid shaped by its own spin and internal mass. Waterfalls are not just about water falling down, but also about energy converting into powerful updrafts that lift mist high into the air. And trees are not just passive giants, but sophisticated hydraulic engineers, using the sun's energy and the unique properties of water to pull life-giving liquid hundreds of feet into the sky. Gravity isn't just a simple force that pulls things down. It's the master conductor of a complex, cosmic orchestra, creating the oddities, the wonders, and the very fabric of the world we live in. It's a force that shapes planets, moves oceans, and enables life to reach for the sky. The world is so much more fascinating when you know where to look. Thanks for joining us on this journey into the oddities of gravity. If you found this as fascinating as we did, don't forget to like this video and subscribe to our channel for more deep dives into the science that shapes our universe. What other scientific mysteries would you like us to explore? Let us know in the comments below. See you next time.